All right. So continuing with our topic on vectors, one of the most common operations that we encounter or we need to perform is the scalar product, also known as the dot product. And the scalar product or dot product of two vectors is defined as this one. So we use the symbol dot, so literal dot. So A dot B, which A dot B means the scalar product of these two. So that is equivalent to the magnitude of the first vector multiplied by the magnitude of the second vector and multiplied by the cosine of the angle between them. Okay, so for example, if this is vector A and this is vector B and they form a certain angle, then their that product is this one. Okay, so um, let's try this example. Okay. We have the vector A having components 1, 4 because it says here the end of this vector is on 1, 4. 1 meaning 1 unit to the right and then 4 units upward. So that means the AX or the X component of A is 1 and AY or the Y component of A is 4. So AX is 1, AY is 4. So you can plug them in here in this formula, Pythagorean theorem, and you got your magnitude for A. Okay, so that's 4.123 because 1 squared plus 4 squared and then take the square root. And same thing with the vector B. We have bx as 3 and by as 5. So just um, substitute them in this formula. So 3 squared plus 20 plus 5 squared equals to this one. Okay. Um, let's go. Oh, don't forget the square root. So square root of 34 is 5.83. Okay, now here comes the hard part or the challenging part of scalar products. Um, the angle. Okay, so we are not um sure of the angle. All right. Um, but we can solve for the angle using this formula. Okay, it's not even here, but we can find it or you can use some trigonometric and geometric principles if you want. But here, since we need you can use this formula, okay? Square of the arc cosine of the square of the magnitude A and square of magnitude B minus the square of magnitude C divided by twice the product of magnitudes A and B. Um, However, the problem here is we don't have the magnitude C. Okay? Magnitude C of our vector. So with that, remember we have the concept of resolving or finding the resultant. So we can use vector sum. We can basically add all the x's. Like here, we have ax and bx. So ax is 1 and bx is 3. So 1 squared plus 3 squared, so that is 10. And then the square root of 10 is 3 point something, I guess. Right, that's for the x. And then for the y, we have, so ax is this one from here. Okay, let me annotate again. So, sorry, cx, I mean. So cx. Why it's not working? Annotate. How do I add? Okay. Oh, right. So this is the x component of C. So we have Cx here. I will not, I will see, I will Cx. Okay, sorry, it takes time. I don't have a drawing pad. Okay, and then we have the vertical component here. Okay, so this is CY. Right? So basically, this is a right triangle. That's why we can then solve for the magnitude C using Pythagorean also. So we just need, again, AX is square root of 10. And, sorry, CX is square root of 10. So I will not write CX, this is square root of 10. And then the CY, how do we solve for CY? Just take the vector sum of the AY and BY. Okay, so AY is 4, so 4 squared plus BY is 5, so 5 squared. 4 squared, 16, 5 squared is 25, so add them together, take the square root, and that's CY. Okay, and then use the Pythagorean theorem to solve for C. Okay, magnitude C. So once you have the magnitude C, then substitute that here. Okay, and you can come up with your angle. Okay, you can solve for the arc cosine of this fraction. Okay, and it appears okay, you can check whatever the resultant C, whatever the magnitude of that resultant, then the arc cosine for that is this one actually, this angle. This is the angle, let's say phi. Okay. Um, all right. For C, this is for angle C. What else? Right. So now that we have the amplitude or the magnitude of 4 of A, magnitude of B, and the theta, then we can now substitute them to get the scalar product. Okay. So it looks simple here, but the challenge is on determining this part, the C. Okay. So if it's not given, you have to derive it from the given coordinates 1, 4, and 3, 5. All right. So I hope you got it. And we'll have more examples in our handout and in our face-to-face discussions. Right? This is just an introduction, by the way. Right. So let's close this. Next, we have the cross product, which produces a vector perpendicular to the plane formed by two vectors. So, for example, using the right-hand rule, which is very helpful in other concepts of physics, especially in electromagnetism, we have A and B. So, cross product of A and B is just the product of their magnitudes multiplied by the sine of the angle between them. Okay, so if this is vector A, okay, you can do so. You can follow the right hand rule for easier, what do you call this, representation or assumption. So vector A is on our, let's say, our index finger, and vector B is our middle finger. Okay, be careful when you are doing this. So that means their cross product is the direction of your thumb. Okay, so the direction of their cross product is the direction of your thumb. Okay, so that is to imagine their cross product vector. Okay, so the magnitude corresponds to the area of the parallelogram formed by the vectors. Okay, so one way to solve for it is to um, solve for the area of the parallelogram, which is actually this one. Okay, just multiply the A and B, and then you get multiply by their sign, and that's it. That's where we got this formula. Okay, this is basically the formula of a parallelogram, area of parallelogram, right? Just take note that the direction of rotation is significant, and that, for example, if we do this way to signify the direction of vectors A and B. For example, vector A is um upward, while vector B is towards that. So the rotation of your hand, if you do it this way, okay, the rotation is from A to B. Okay. But if you reverse that, take note, it will not be equal unless you put a negative indicator, okay, or a negative sign. Okay. Therefore, the cross product of two vectors is equal to the negative of their cross product, or cross product of their reverse operation, or reverse direction. Okay, if counterclockwise is b times a, therefore that is equals to the negative of the clockwise direction. Okay, we have an example here. This one is easier because the angle is given. All right. So we have magnitude A and magnitudes B already given. So we have 10 and 13. Just multiply them and then multiply with the sign of the angle between them, 59.5. And you can double check. That would be 65.89 units. Okay. So if the if the angle is not given, you can derive using what we did, using the method here, what we did to solve for the angle. Okay, using the cosine rule. Um, yes, you can use your trigonometric formulas actually to determine any unknown values here. Okay, so what else? Okay, I hope you get the concept of dot product and cross product. We're going to have some more illustrations in our face-to-face discussion and our in our handouts. Okay. Now, we were talking about, okay, I forgot to move this. We were talking about coordinate, or we were mentioning coordinate system. Take note that there are different types of coordinate system, and coordinate system basically provides a reference framework for expressing vector quantities numerically. And the common systems that we use, especially in engineering, are, okay, number one, of course, the Cartesian or the rectangular coordinate system, or the XYZ coordinate system. So we define them by mutually by or defined by mutually perpendicular x, y, and z axis. So um X and Y axis are perpendicular to each other, Y and Z axis are perpendicular to each other, and X and Z axis are perpendicular to each other. So it is the most widely used system in electronics and ICT due its compatibility with circuit layouts, simulations, and numerical solvers. Okay, so actually we've been using the rectangular system since module one, right? But for higher physics, you're going to see soon that you're sometimes you have to use the polar and the cylindrical coordinate systems. Okay, they are useful for problems involving radial symmetry, such as in antenna radiation patterns, rotating machines, and circular waveguides used in telecommunications. Okay. Um, Likewise, we have the spherical coordinate system, which is applied in electromagnetic field analysis, satellite communications, and 3D radiation modeling. Okay, because we have to take note that most electronic simulations internally convert non-Cartesian coordinates into Cartesian form for matrix-based computation. Basically, there's when you study these other coordinate systems, one of the most important concepts that you must learn is how to convert them into not Cartesian, uh, Cartesian equivalents, so that we can then convert them into matrix form. Okay, they have their matrix forms because that's what our computers can understand. Okay, um, the matrix form matrix. uh, when we input our vectors in terms of matrices, the computer will then convert them, of course, into binary, and then they can process it. Okay. So again, polar, cylindrical, spherical, we convert them into Cartesian, and then Cartesian, we convert it to matrix form. Okay, so soon you're going to have encounter more of these, but for now, it's important to understand that there's more to Cartesian coordinate system. Okay, it's not the only coordinate system that we must study. Okay, but for now, okay, we use this one. Okay, we focus on this one. Right? So I mentioned the matrix. Take note that vectors are naturally represented in matrix column, especially in computational analysis, or meaning with the help of the computers. Um, okay, it's vital in engineering computation. So for example, if you have the vector A represented as AXI plus AYJ plus AZK, we can actually represent this as this one. So especially the magnitude. So the magnitude of vector A is actually the matrix, the column matrix of AX, AY, and AZ. Okay. So what else? Right. So we have such thing as matrix algebra as part of linear mathematics, linear algebra mathematics. Um, when we represent a scalar value in matrix form, actually we only have a zero-way tensor. Okay, so just one. Think of it as one cell in a table. Okay, so but when we have a vector, we now have a one-dimensional. Okay, we now have a 1D or one-way tensor. Okay. Tensors are actually the somewhat like the building blocks in in machine learning. Okay, machine learning applications. So the processings are usually in terms of tensors, and uh, okay, that's how our computers take care of vectors. Okay, if you have a two-dimensional tensor, your vector now has a horizontal component, or rows. Okay, so multiple rows, or multiple columns rather. Okay, so it's not just one column, but multiple columns. Usually we use this in higher mathematics. And for example, you have three equations, three unknowns. You can represent that into a matrix. Okay, so for example, if you have three vectors involved in your given scenario, then actually you can represent them as a matrix. Okay, so if you take it further, you have the three-way vector, four-way vector, and so on. Of course, they will be too much already for us. Okay. Um, actually, in engineering, in our case, we normally focus on this portion only, up to two-way tensor. But for advanced machine learning applications, then you have to try to understand the higher levels of matrix algebra. Okay, this representation simplifies vector operations, and it enables direct use in linear algebra operations, numerical simulations, and control system and signal processing algorithms, especially using machine learning applications. So most engineering software like MATLAB, Python, Spice-based solvers operates on vectors and matrices rather than geometric drawings. We cannot input drawings directly. Instead, what the computer will do, it will scan the drawing and then represent them in terms of uh, matrices in the form of uh, I mean, it will scan the drawing, determine the vectors, and then convert the vectors into their matrix form so that it can perform the necessary calculations. Okay. Um, This is critical in optimization, filtering, and machine learning systems embedded in modern ICT infrastructures. So, okay, I hope you now have a vision on on where can we use vectors actually, especially as ECEs or as someone in the ICT field. Vectors are foundation actually when it comes to machine learning and other similar applications. Okay. In engineering systems where quantities vary with space and time, take note, vectors are often functions rather than constants. That's why we have calculus-based vector operations that allow us to analyze how vector fields change, interact, and propagate. So this is an essential capability in electronics, communications, and control systems. So we can think of vector as a position vector, a position quantity, position physical quantity. Okay, so for example, we have the vector r, and in terms of time, we can write it as this one. So the position can have in Cartesian coordinate system, it can have an x component, a y component, and a z component. So just like what we had earlier, the x component is paired with the I unit vector, y paired with the j unit vector, and the z paired with the k unit vector. Okay, so when we are taking derivatives of the r or the position vector, we yield to physically meaningful quantities like the velocity. Okay, you take the derivative of the r, you get this one, the derivative, the velocity. Okay, same in the same way, if we take the derivative of the velocity, we get the acceleration, or we can derive it using this one. Okay. Um, Okay, and you can study this representation on the right side, right? Okay, I guess. All right. So before we move to the next concept, let's talk about some other important physical quantities that are also considered as vectors, and therefore that they involve also vector analysis. Okay, so position vectors establish the mathematical description of location in space, which is fundamental when introducing mass and weight as physical quantities whose influence depends on spatial distribution and line of action. Okay, so before we talk about those things, let's define first mass and weight. They are in common language, we are um, using them synonymously with each other. We are interchanging them. But actually, if we get more technical, we shouldn't do so because mass is a scalar quantity that represents the amount of matter in a body and its resistance to changes in motion. Okay, so an object has the same mass wherever it goes. Okay, as long as uh none of its parts gets removed. Okay, as long as it stays intact, 100% intact, wherever it goes, the mass will remain the same. Okay, which means whatever your mass in on Earth, that will also be your mass in space or in other planets. All right. Whereas we have the term weight, which is a force vector. So vector is another thing that we're going to talk about in the next slide. It is a force. Weight, just remember, mass is a scalar quantity while weight is a vector quantity because it is a form of force. Okay, and that force is associated with the mass due to gravitational influence. So you have your mass, and because of the gravitational pull, which has an acceleration of 9.81 meters per second squared, then your mass now becomes your weight. Okay, so just imagine it. as this one using this illustration. If you have a 36 kilogram mass on Earth, then multiply it by 9.81, so you have approximately equals to 316 Newton weight. So technically, when someone asks for our weight, we should answer in terms of Newton. But we had been used to it. We got used to it that weight is measured in terms of kilograms. Okay, because it has been accepted eventually. We that's why we have the terms kilogram mass and kilogram force. Okay, so okay, so okay. Sorry for that interruption. Um, Okay. Again, as I was saying, if you have a mass on Earth, or if you have a mass of 36 kilogram, then your weight on Earth is around 360 Newton. Okay. But if you go to the space, especially on the moon, your mass is still 36 kilogram, but your weight is now 60 newtons. Okay. Why? Because this G, okay, the acceleration due to gravity is different on other areas of space. Okay, on Earth it is constant around approximately about 9.81 meters per second squared. Okay, so the acceleration due to gravity, by the way, represents the gravitational influence that causes mass to experience weight. Okay, so whenever there's a mass on Earth, anything on Earth that has mass automatically has a weight. Okay? Everything on Earth is being pulled down by gravity. Okay? Everything on Earth experiences 9.81 meters per second squared gravity, except for some areas like the in vacuum, inside the vacuum. Um, that's a different story. Okay? So force, by the way, although we're going to talk more about this in module 4, we're going to have a formal force about or topic about motion. So for now, take note that force is just derived using this equation. Okay, just multiply the mass by the acceleration acting on it. Okay, so just like us, we have our mass, and the gravity acts on us with this acceleration. So basically, we have, for example, if your mass is 36 kilograms, you just multiply it by the gravitational constant, G. Okay, so force equals to mass times acceleration is somewhat like weight equals to mass times G. Okay, and it's always that way. Weight is always downward, okay, downward and never in any angle. Regardless of your position, regardless of the surface you are on, weight remains at, I think, 270 degrees with respect to the positive x-axis. In short, downward, straight downward direction. Okay, so for other forces that are except for the weight, we use the formula F is equals to ma, and we're going to talk about that in the next modules. In the meantime, let's formally introduce force, okay, before we end this part and then move to the next section. Okay. Force, we already mentioned it a while ago. It is a vector quantity characterized by magnitude, direction, and point of application. So, we're going to have a more formal and more detailed um, discussion about force in one of our next topics. But for now, take note that force are somewhat something that pushes or pulls an object. Okay, so something like that. And force can be differentiated or can be classified as either a contact force or a non-contact force. So contact force, interactions between objects that touch. Okay, non-contact forces, those are that attract or repel even from a distance. Okay, example of contact forces that we normally experience in life, in our daily lives, are applied force, the one that we directly apply, or the spring force whenever many of our machines have springs on them. And of course, that's another type of force or drag force. Try to whenever a vehicle runs um through a windy environment, it actually experiences drag force, which could lessen its speed. Okay, the faster that car goes, the more drag force it experiences. Okay, and in solid surfaces, we have the frictional force. Uh, of course, just like drag force, it slows down whatever object is moving. Okay, so also whenever there's a weight, the sur the surface where the object is placed on will apply normal force. Okay, why? Because it is something that opposes the force due to gravity. So imagine if you're sitting on a chair and there's no normal force. If you're sitting on a chair, you're going to go straight downward forever. No one's there to stop you. Okay? But because of the normal force applied by that surface, it will stop you. It will make you stay on that level, on that position in a chair. Okay. Some non-contact forces are magnetic force, electric force, gravitational force. Actually, we can classify them further as the four fundamental forces that govern the behavior of matter in the universe. So we have the strong force, which is actually the force between our atoms, or the particles within our atoms, which are the protons and neutrons. Um, Okay. So, or we can say the nucleus. Protons and neutrons form the nucleus. So that is made possible through the strong force between them. Okay. Whereas the attraction between the nucleus and electrons is called electromagnetic force. And that is the main basis of our other fields of physics like electromagnetism and electricity. Okay. We also have the weak force and the gravity. So we mentioned already the gravity, and then the weak force is somewhat new, somewhat too technical for us, or too different from our perspective. Weak force changes protons to neutrons and vice versa, emitting radiation. All right, so that's already beyond our scope. Right? In the meantime, take note that in engineering models, forces acting on extended bodies are often assumed to act at the centroid or the center of mass to simplify analysis. And we're going to talk about that in the next section. Um, Take note, by the way, that forces, since they are vectors, can be represented similarly. Okay, so a vector F, which represents our force, can be written as in terms of its x, y, and z components with their respective unit vectors. Okay, same thing. X is to I, y is to j, and z is to k. Okay, so you can I will not discuss this because we are going to have a formal discussion on force. I just introduce force because some of our examples in the next section will involve force. Although the uh how it relates to motion, we're going to do elaborate them further, or we're going to have a formal discussion about them in our next two modules. Okay. Um, in the meantime, you can observe these representations. Okay, vectors. Force is basically a vector. So whatever we talked about earlier about vectors can also be applied on forces. Okay, so we analyze also forces in the same way that we analyze most other vector quantities. Right?